Okay, we are back. I got some interesting questions for you. Or tasks, rather. The first task is to prove that the limit as x approaches negative infinity of this beast is equal to root 2 over 7. So, if this were like thrown at you in a test setting, you can't just be like, yeah, the shortcut tells me this is the answer. It's, you are showing me the process by which you break this thing apart. Maybe breaking apart's not the right term. But here's what we do. Remember, you're supposed to divide by the greatest power in the denominator, and then it has its equivalent root value up here. So, for instance, x is equal to the biggest power on the bottom. But that is the same as root x squared. So if I divide by x on the bottom, then I have to divide by root x squared on top, because x's can't interact with root x's in division until you create it as a root. Now, you also have to keep in mind that whenever you take a square root of an even power, and it becomes odd, because 1's an odd number, then it's actually the absolute value, which is x when you're approaching positive infinity, and negative x when you approach negative infinity. So there's a lot going on here, but it's actually a very easy thing to prove. Because right here, all we're doing is saying, look, we need to find some way of using this negative infinity. So I'm going to divide the bottom by negative x. Okay? That's the one, it seems to be a problem of sinking in with a lot of students why we're dividing by negative x. But hopefully that kind of explains it better. The top. Now, here's the deal. In no way did I say to divide by negative x squared. You were dividing the top by root x squared. Okay? And when you take a square root divided by a square root, the two separate roots become one and the fraction gets absorbed inside. So it's like, no, you're gone. And then everybody inside the square root, all right, is now being divided by x squared. So this is being divided by x squared, this is being divided by x squared, and this is being divided by x squared. So now we do some simplifications. Basically, the top x squareds cancel, so you have a 2. And x on top here cancels with one of them on the bottom, minus 5 over x. This is just 2 over x squared. On the bottom is negative 6 over x. And then negative 7 divided by negative x is positive 7. All right. One final move. Remember, this was a limit. I should have put my limit notation right here. Shame on me. But there's grace for that. So when you plug in a giant, a never-ending, like this is negative infinity. So it's going further and further negative in value forever. 80 trillion to the 80 trillionth power kind of infinity. Yeah, it's big time. It's going to zero out anybody who's got a bigger power on the bottom than it does on top. And since this strategy created constants on top and powers on the bottom, you can just say, whoever's got an x on the bottom, you got to go. You're going to zero out. So this is 0, this is 0, and this is 0. Leaving us, so when I apply the limit as x approaches negative infinity, it zeroes out these quantities and leaves us with root 2 over positive 7. Well, what do you know? We proved it. Wow, proofs are intense. Let's do another one. So prove on number 10. We basically have done this. I just wanted to see if somebody knew how to put all the steps together. So show that this is going to be negative infinity. So really, all I was asking you guys to do for this was show how this how it decomposes, the decomposition of it. So this is x minus 7 over, you can factor an x out of these two terms. Then you would try to take out, so to speak, or let's just say rewrite the function. Rewrite the function as the limit as x approaches 6 from the right of 1, it's on the bottom, 1 over x minus 6. And then we'd multiply that by x minus 7 over x. Same thing, we're still applying a limit to it. All right, positive means you're going to get positive infinity for that part. This one should just be a constant value. So 6, plug it in here and here. Little scratch work, you get 6 minus 7 over 6, which is negative 1/6. So negative 1/6 of infinity, you just call that negative infinity because operating a constant negative value to a positive infinite value yields a negative infinite value. You can't see that, can you? Oh, you can see that. Hey, we proved it's negative infinity. All right, number 11. Compare and contrast the continuity between the two functions below. So I always find it interesting to see how students will try to use reasoning skills through, the English language instead of just doing everything mathematically. That's why I think this showed up on this particular version of the test. Well, when we look at f of x, the top is a difference of squares in which one of those one of the parts of that square cancels with the bottom. So f of x is equal to 5 plus x with a hole at x equals 5. With a hole at x equals 5. On the right, though, it seems like when I take the limit as x approaches 5 from the left, that would be the bottom less than. Yeah, you plug in 5 for the x, it's 5 plus 1 is 6. And on the top, that would be the limit approaching 5 from the right. 5 minus 2 is 3. This would be a situation where this limit does not exist. Okay? This has a break at x equals 5. Now, right now, this is just sort of like looking at the situation from our mathematics standpoint. It says to compare and contrast the continuity between the functions below. And it says be sure to talk about removability. So it's actually a very simple explanation. The function f is, because it's a whole, it's removably discontinuous at x equals 5. Removably discontinuous at x equals 5. Whereas g of x is non-removably discontinuous because, look, the break means that they would not converge to the same spot. discontinuous at x equals 5. Yeah, that's pretty much it. That's all you had to do. That's the most concise, the most elegant way in which to express that. All right, so speaking of continuity, the bottom section is the last of it all. And it's all about continuity, the computational type. So, oh man, let's see, 5 examples in 4 minutes and 15 seconds? I don't think that's going to happen. Too many videos. Let me do one example and then I'll restart this business. All right, number 12. I'm trying to determine how continuity works with the function f of x is equal to x squared minus x over x cubed plus 7x squared minus 8x. All right, so here's what we got to do. We got to determine which parts of this function have asymptotes and which have holes in the graph. So it looks like this one's like a classic factoring example. The numerator factors an x out. The denominator factors an x out. You're left with a trinomial right here. And then you ask yourself, hey, is this thing factorable? Maybe more stuff's going to cancel. The answer, yeah. X squared plus 7x minus 8, if we need to go through the long way, we ask ourselves what multiplies to give us 1 times negative 8 and adds up to give us 7. Well, 8 times negative 1 would give us positive 7. So I could technically split this up into negative 1x plus 8x, which would be x squared minus 1x plus 8x minus 8. Group the first two together, take an x out, x minus 1 remains. Group these second two together, take an 8 out, x minus 1 remains. It's x plus 8, x minus 1. By the way, notice there's a shortcut for factoring. 8, negative 1, 8, negative 1. If the leading coefficient's a 1, it does that every single time. So, store that up there. So then, you get x times x minus 1 over x times x minus 1 times x plus 8. Which reveals to us the factor of x equals 0 cancels out. The factor of x minus 1 equals 0 cancels out, leaving us with the function f of x equals 1 over x plus 8. That's a function with an asymptote at x equals negative 8, in which x equals 0 yields a hole in the graph, and x equals positive 1 yields a hole in the graph. So what do we got here? We have 2 removable discontinuities. It's removably, what am I doing? I'm just going to put RD. Removably discontinuous at x equals 0 and x equals 1. It's non-removably discontinuous at x equals negative 8.